Hello everyone, so today in this video we're going to be talking about vapor-liquid equilibrium. So this is the first video depending on the liquid-vapor equilibrium, and for the first part of the video we will be talking about bubble temperature and pressure and dew temperature and pressure and why are they important. So before going into the main concept, we should probably talk about Raoult's law and Antoine equations. So we had previous videos depending on Antoine equation, right? So the Antoine equation was the pressure in log base 10 should be equal to A minus B over C plus T, right? So we use that with the vapor-liquid equilibriums to determine the specific pressure at a specific temperature. So now we have another law which is called the Raoult's law. So it has an equation of Xi times Pi saturation Yi times P. So what Raoult's law states is the mole fraction of components in liquid phase, which is Xi, times the pure saturation pressure, which is the PiSAT, should be equal to the product of mole fractions in vapor phase multiplied by the total pressure, which is the sum of all the partial pressures. So we're going to be using these two equations to determine the bubble temperature and pressure and dew temperature and pressure. So let's just start with the bubble temperature. Let's start with the bubble pressure first, then it's going to be easier for us to determine the bubble temperature. So what is the bubble pressure? So bubble pressure is the pressure at which the first bubble of gas occurs in when the first bubble of gas is formed and at a specific in a given temperature for a mixture of liquids. So it's going to be the special temperature at which the first bubble occurs. Okay, let's imagine we have a system with piston. Okay, and we will have what? So we will have a mixture inside. So we can have a mixture of let's say 30 mole percent of benzene and 70% of toluene. And we're given the pressure and temperature, which is going to be 323. Let's say this is our given temperature and pressures. And we're going to use this piston idea to find the bubble and dew temperature and pressures. So in order to have the bubble occurred, we should heat up the piston. So we're going to move the piston up, and it might result the change in temperature, right? So it might result the decrease in heat. So we should heat it up so that we remain the same temperature. We remain in the same temperature. So for the dew temperature and pressures, we should move the piston down, and it's going to increase the temperature so that in order to have the constant temperature, we should cool it down so that we don't have any temperature changes. So for the bubble pressure, we have the liquid mixture, and the sum of the mole fractions in liquid phase should be equal to 1. So we have equation. So from the Raoult's equation, Yi, which is the mole fractions of the components in liquid phase, should be equal to 1. So now we have this equation, let's just specify it. So it is bubble pressure. So for the bubble pressure, we have Xi times pure saturation pressure should be equal to the total pressure, because as we said, the sum of the mole fractions in liquid phase should be equal to 1, sorry. And so our pressure, our bubble pressure, should be equal to the sum of partial fractions, which is this one in our equation, and which is going to be the sum of all mole fractions of components in vapor phase multiplied by their pure saturation pressure. And this is going to be our bubble pressure. And for the bubble temperature, so for the bubble temperature, it's the temperature when the first bubble is formed in a mixture, in a liquid mixture. So we're going to use the same idea. Again, the mole fractions in liquid phase, mole fractions of components in liquid phase is again equal to 1. So we have again the same equation here, but this time we are given with the pressure. This time we're given with the pressure, and we're asked to find the temperature. Okay, so for that equation, we can use the bubble pressure equation, but we can change the saturation pressure, pure saturation pressure, using the Antoine equation. So for the bubble temperature, we have another equation, which is going to be, again, the total pressure must be equal to the sum of the partial pressures, which is going to be equal to, again, the mole fractions in vapor of compounds in liquid phase, in vapor phase, multiplied by the pure saturation pressure, but we're going to replace that using the Antoine equation. So it's going to be 10 to the power of A minus B over C plus D. And this is going to be our bubble temperature. Let's highlight it so that it's easier for us to find it when we will be working with the code. Okay, so this was the bubble temperature and pressure. And now let's look at the dew temperature and pressure. So let's start with the dew pressure. So the idea stays the same. We're going to be using the Raoult's equation, Raoult's law again, but this time dew pressure is the pressure at which the first liquid drop is formed at a vapor mixture, at a given temperature for a vapor mixture. So this time our Xi, which is the mole fractions of components in vapor phase, should be equal to 1. So our sum of Xi should be equal to 1, and our sum of mole fractions in of components in vapor phase should be equal to the sum so from the Raoult's law, if we solve for Xi, we will have equation Yi like mole fractions of components in liquid phase times the pressure over pure saturation pressure. So now we have this equation here. As we know, this is going to be equal to 1, right? So now we can use this idea and solve for pressure, so that if we manipulate this equation, we have this equation here, which is going to be Iy over pure saturation pressure. And this is going to be the equation for the dew pressure. So again, the idea stays the same this time, as we're trying to determine the dew pressure. We're going to say that the mole fractions of components in vapor phase is equal to 1. So now let's move to the dew temperature. As we're solving for the temperature, we're going to do the same thing as we did for the bubble temperature. So we use the same equation and replace the pure saturation pressure with the Antoine equation. So for the dew temperature, it's going to be the same equation, and we're going to replace the pure saturation pressure with the Antoine equation plus, it's minus BC plus T. And we have an equation for the dew temperature. So in this video, we looked at the idea of bubble pressure and temperature, and dew pressure and temperature, and derived the equations for each of them, so that in the later videos we can try to write a code that we will be able to calculate the bubble pressure and temperature and dew temperature and pressure at a specific pressure and temperature at a given temperature for the mixtures with n components. So thanks for your attention.